Welcome. Today, we're diving into fluid mechanics, the study of how liquids and gases move and interact. It's a field that touches everything from weather patterns to airplane design. Let's explore the principles that govern flow, pressure, and forces in fluids, and see why they matter in the world around us. Let's take a step back and look at the big picture of fluid mechanics. We're covering everything from the basics, like pressure, buoyancy, and stability, to more complex ideas like laminar and turbulent flows. We'll explore both liquids and gases, and how their properties like density, viscosity, and compressibility shape their behavior. This course will guide us through fluid statics and dynamics, helping us understand the forces at play when fluids move or stay still. It's a broad field, but we'll break it down step by step. Fluids share some key characteristics that set them apart from solids. Their molecules are spaced farther apart, making them less tightly packed. The forces holding these molecules together are relatively weak. Because of this, fluids can't resist shear stress when they're at rest. They simply flow. They also take the shape of whatever container they're in, adapting seamlessly. We usually think of fluids as continuous materials, and one of the main ways we tell different fluids apart is by their viscosity, how thick or runny they are. Density is a measure of how much mass is packed into a given volume of a fluid. We usually write it as mass divided by volume. Sometimes we talk about specific volume, which is just the flip side, volume per unit mass. Different fluids can have very different densities. For example, water at 4 degrees Celsius has a density of about 1,000 kilograms per cubic meter, while air at the same temperature is just over 1. Liquids don't change density much with pressure or temperature, but gases can vary quite a bit. Let's talk about specific weight. It's the weight of a fluid per unit volume. We calculate it by multiplying the fluid's density by the local acceleration due to gravity. For most practical purposes, that's about 9.807 meters per second squared. Specific weight helps us understand how heavy a fluid system really is. For example, water at 4 degrees Celsius has a specific weight of 9.8 kilonewtons per cubic meter, while air at the same temperature is much lighter, just 11.9 newtons per cubic meter. This concept is key when measuring fluid mass and weight. Let's talk about specific gravity, a way to compare how heavy fluids are without worrying about units. It's a ratio, plain and simple. We take the density of the fluid, then divide it by the density of water at 4 degrees Celsius. Water's density there is a nice round 1,000 kilograms per cubic meter. For example, mercury has a specific gravity of 13.2, meaning it's over 13 times denser than water. This ratio helps us understand fluids, weight relative to water, no matter the units used. Let's talk about viscosity, a key property that measures how fluid or thick a liquid really is. It's not just about density or weight. Instead, viscosity tells us how a fluid resists shear, or how it flows when force is applied. When you push on a fluid, it starts to move, and the relationship between the force applied and the fluid's velocity change is captured by viscosity. This helps us understand everyday fluids like water, air, oil, and gasoline. Let's take a closer look at how we measure viscosity, the resistance of a fluid to flow. One common tool is the capillary tube viscosimeter. It works by timing how long a fluid takes to pass through a narrow tube. Viscosity isn't the same for every fluid, and it changes with temperature, so we always measure temperature alongside it. The units we use are Newton seconds per square meter or pounds seconds per square foot. Coming up, we'll see a movie example showing this in action. Let's talk about fluids and how they behave under stress. Newtonian fluids follow a simple, linear relationship between stress and strain, meaning their viscosity stays constant no matter how much force you apply. Think of water or latex paint. On the other hand, non-Newtonian fluids don't play by those rules. Their viscosity changes depending on the stress, like toothpaste or corn starch mixtures. Understanding this difference helps us predict how materials flow and respond in real life. It's all about the relationship between force and flow. Kinematic viscosity is just another way to look at viscosity, especially when we're dealing with flow equations. Instead of the usual units, it's measured in terms of area over time, like meters squared per second, or feet squared per second. It's basically the ratio of dynamic viscosity to density, giving us a sense of how a fluid flows under gravity or other forces. This concept helps us understand fluid behavior in a more practical way for engineering and physics. Let's talk about bulk modulus, a measure of how pressure affects a fluid's volume or density. It's expressed in units like pascals or psi. When the bulk modulus is large, it means the fluid is nearly incompressible. In other words, you need huge pressure to squeeze it even a little. For example, water requires over 3,000 psi to compress by just 1% at room temperature. That's why, for most engineering purposes, liquids are treated as incompressible. Let's talk about how gases behave under different conditions. We use pressure, density, temperature, and the gas constant to describe these changes. In an isothermal process, temperature stays the same, so pressure and volume relate in a specific way. For an isentropic process, where there's no heat exchange or friction, the relationships shift, involving the ratio of specific heats. Interestingly, air is about 15,000 times more compressible than water, but in many engineering cases, we still treat air as if it's incompressible. This helps simplify calculations without losing accuracy. Let's talk about the speed of sound in fluids, starting with the ideal gas law, where C equals the square root of K times R times T now, in an isentropic process, which means no friction and no heat exchange. Small disturbances in the fluid travel at a finite speed. These pressure waves move as sound, and that speed is what we call the acoustic velocity, or simply, C it's linked to how compressible the fluid is, and we can express it in terms of pressure and density changes. This concept is key to understanding how sound moves through different fluids. Let's talk about the speed of sound in different fluids. At 60 degrees Fahrenheit, sound travels roughly 11-17 feet per second in air, but much faster in water, about 48-60 feet per second. This difference happens because fluids compress slightly, and if a fluid were truly incompressible, sound would travel infinitely fast. For example, a jet flying at 250 meters per second at high altitude, where it's much colder, moves at a speed close to the local speed of sound, which here is about 297 meters per second. This ratio helps us understand how compressibility affects sound and flight. When an object moves faster than the speed of sound, that's when things get really interesting. We see shock waves and those famous sonic booms. This slide shows a wind tunnel visualization using the Schlieren method, which makes these shock waves visible by capturing condensation caused by the jet's speed. The key concept here is the Mach number, the ratio of an object's speed to the speed of sound. Below one, we have subsonic flow. Above one, supersonic flow. In this example, the ratio is about 0.84, just under the speed of sound. Let's break down what's happening when a liquid evaporates. At the surface, some molecules have enough energy to break free from the pull of their neighbors and escape into the air. This creates vapor, and that vapor pushes back on the liquid, which we call vapor pressure. Vapor pressure depends on temperature and the type of liquid. Now, boiling happens when the pressure inside the liquid matches this vapor pressure. That's why water boils at 100 degrees Celsius at sea level, but at higher altitudes, like Colorado Springs, it boils at lower temperatures. Cavitation is a special case of boiling caused by low pressure in flowing liquids. Surface tension is what creates that thin skin on a liquid surface. Inside the fluid, molecules pull evenly on each other. But at the surface, there's a net inward force. Molecules are pulled tighter together, almost like a stretched membrane. This tension depends on the type of liquid, the temperature, and what's touching it. We can break this membrane with surfactants, which lower the surface tension and disrupt that tight bond. It's this delicate balance that lets the surface support weight and shape. Let's look at how surface tension works around a liquid drop. The force created along the edge of the drop is due to surface tension, acting like a tight skin. This force balances the pressure difference between the inside and outside of the drop. We use the radius of the drop and the surface tension value to calculate this force. By drawing a free body diagram, we can model the pressure inside the drop mathematically, helping us understand how these forces interact in real fluid drops. Let's look at how surface tension relates to pressure inside a liquid drop. The key idea is that the pressure inside the droplet is higher than outside. That difference is always positive. By balancing the force from surface tension with the pressure force, we get an expression for this pressure difference. Now, here's a challenge. Think about a bubble of water. Would its internal pressure be greater or less than that of a droplet? It's a subtle but important distinction to explore. Let's talk about capillary action, the way liquids move in tiny tubes. It all comes down to two forces: cohesion, which is how the liquid molecules stick to each other, and adhesion, how they stick to the tube's surface. When cohesion is stronger, the liquid pulls together and can resist climbing the tube. But when adhesion wins, the liquid climbs up, wetting the surface. This balance creates that familiar rise or fall of liquid in small tubes, driven by surface tension and the contact angle between the liquid and the solid. Our goal here is to measure how pressure drops along straight sections of pipes, whether they're smooth, rough, or packed, and see how this changes with flow rate. We'll connect these observations to friction factors and Reynolds numbers, key concepts in fluid flow. Then, we'll compare our results with existing theories. We'll also look at how pipe fittings affect pressure drop, and finally, explore how flow area relates to pressure loss in devices like Venturi and orifice meters. This gives us a full picture of flow in circular pipes. Here, we see the key apparatus involved in our setup: pipe networks, rotometers, and manometers. Each plays a vital role in measuring and controlling fluid flow. The pipe network directs the flow, the rotometers give us precise flow rates, and the manometers measure pressure differences. Together, they form the backbone of our experimental system, letting us observe and analyze fluid dynamics in action. Fluid flow in pipes plays a crucial role in many areas of our lives. It's the way blood moves through animals and plants, how water reaches our homes, and how cities manage irrigation and sewer systems. Fluids can be simple, like just liquids or gases, or more complex mixtures of solids, liquids, and gases. Some fluids behave predictably, like water in your experiment. Others, like mayonnaise or polymer melts, don't follow those same rules. Today, we'll dive into the theory behind these different types of fluid flow. To understand these flows, we start with two fundamental principles: conservation of mass and conservation of momentum. These equations give us a general framework to describe how the system behaves dynamically. The main challenge is linking the flow rate to the pressure drop across the system. Now, when the fluid is Newtonian, isothermal, incompressible, steady, and laminar, the analysis simplifies. In laminar flow, velocity moves in a single direction, making the math more manageable. This sets the stage for a deeper theoretical discussion. Let's talk about what happens when fluid flows through a fixed volume and forces act on it. According to Newton's second law, these forces have to balance out. This balance is captured by the Navier-Stokes equations, which describe the flow using velocity and pressure. When we solve these equations exactly for laminar flow, we get the Hagen-Poiseuille relation, a fundamental result that tells us how fluid moves smoothly through a pipe under pressure. Here, we're looking at the forces in play within a fluid flow, specifically laminar flow. We see three main forces: shear forces, pressure, and body force. These forces must balance each other for the flow to remain steady and smooth. When they do, the fluid moves in orderly layers without mixing, which is what we call laminar flow. Understanding this balance helps us predict how fluids behave under different conditions. Let's keep this in mind as we move forward. Let's talk about laminar flow, a smooth, orderly movement of fluid where layers slide past each other without mixing. Momentum here is mass times velocity. When we look at momentum per unit volume, it's density times velocity. The rate of flow of momentum involves how much momentum passes through a given area over time. In laminar flow, velocity at a fixed radius stays constant, which simplifies the calculations. This sets the stage for understanding how fluids behave in controlled, steady conditions. Let's talk about Hagen-Poiseuille flow, a classic example of laminar flow in action. This describes how a fluid moves smoothly through a pipe, layer by layer, without mixing. It's steady, predictable, and follows a precise mathematical relationship. Understanding this helps us control flow in everything from medical devices to industrial systems. It's a fundamental concept that sets the stage for more complex fluid dynamics. Let's continue exploring how this flow behaves and why it matters. When fluid flows faster, it stops moving in smooth, steady lines. Instead, the flow becomes chaotic and unpredictable, what we call turbulence. In this state, the flow changes over both space and time, with constant fluctuations. Because of this complexity, every term in the Navier-Stokes equations matters, making it impossible to find a simple solution. The pressure difference depends on many factors: diameter, viscosity, density, length, and velocity, all interacting in a complex way. Let's talk about the forces at play in fluid flow: viscous forces and inertia. These forces compete, and their balance is captured by something called the Reynolds number, or Rhe. It's a ratio involving density, velocity, and a characteristic length. All the parameters we've discussed so far come from three fundamental dimensions: mass, length, and time. From these, we can create dimensionless groups that help us understand complex behaviors like turbulent flow. This gives us a powerful way to predict how fluids move. Let's break down how fluid moves through a pipe, focusing on the forces at play along the pipe's perimeter, what we call the wetted perimeter. We use the hydraulic radius, which relates the cross-sectional area to this perimeter, to understand flow behavior. For turbulent flow, the friction factor depends on the Reynolds number, showing a specific relationship. In laminar flow, the Hagen-Poiseuille equation governs pressure drop and flow rate. Ultimately, the friction factor links pressure loss to the forces acting on the pipe walls, helping us predict flow resistance in different conditions. When flow becomes turbulent, things get interesting. At high Reynolds numbers, the stabilizing force from viscosity is small compared to the destabilizing force from inertia. This means any small disturbance can grow into large, swirling motions called eddies. These eddies draw energy from the main flow, then pass it down to smaller and smaller swirls. Eventually, the tiniest eddies lose their energy through viscosity, turning it into heat, what we call head loss. This process is the heart of flow instability in turbulence. Turbulence stirs things up inside a pipe. It moves momentum from the center out toward the edges, mixing the fluid as it goes. This mixing keeps the velocity in the center more uniform than in smooth, laminar flow. Near the pipe wall, the swirling motions, or eddies, get smaller, shrinking in size the closer they are to the boundary. This slide shows how velocity spreads out in turbulent flow, revealing a very different pattern than what we see in calm conditions. Now, we're introducing an additional dimensionless group, epsilon over d, that needs to be characterized. This means our friction factor versus Reynolds number plot will show more than one curve. Depending on whether we're in the laminar region, we might use a Fanning diagram or a Moody diagram. For the lowest Reynolds numbers, if the laminar flow corresponds to F equals 16 over Rhe, that's a Fanning chart. If it's F equals 64 over Rhe, that's a Moody chart. Surface roughness also plays a role here. Here, we're looking at a key condition for rough pipes, when the ratio of the pipe's roughness to a certain flow parameter is less than 0.01. This slide introduces a transition function that applies to both smooth and rough pipes. It covers smooth pipes when the Reynolds number is above 3000, as well as rough turbulent flow. We'll also explore how the friction factor behaves in smooth pipes during the transition phase. This sets the stage for understanding flow resistance across different pipe conditions. Here, we see a set of equations related to fluid flow and friction factors. These formulas help us understand how resistance behaves in pipes and channels, especially when dealing with different flow regimes. The Fanning diagram, mentioned here, is a useful tool that visualizes this relationship, making it easier to predict pressure losses. Together, these expressions give us a way to calculate friction factors based on Reynolds numbers, which is key for efficient fluid system design. Let's talk about pipe roughness, represented by the symbol epsilon. This value is dimensionless, meaning it has no units. It's a pure number that tells us how rough the inside surface of a pipe is. Different materials have very different roughness values. For example, Smooth materials like glass or copper have tiny roughness values, while something like corrugated metal is extremely rough. Understanding this helps us predict how fluids flow through pipes, which is crucial for engineering and design. When we're dealing with flow through an empty pipe, the usual equations just don't cut it without some serious tweaks. But once we introduce particles, like in a packed bed, the behavior changes. The Ergun equation helps us understand this. It shows how pressure drop relates to flow velocity, especially at low and high Reynolds numbers. Here, the Reynolds number depends on particle size, fluid properties, and how much space the particles leave open. This gives us a clearer picture of flow in these more complex, packed systems. Valves play a crucial role in controlling flow, but they also introduce energy losses. This happens because the flow path inside a valve is often complex, causing a drop in pressure known as head loss. In fact, one of the reasons valves exist is to create this loss when they're partially closed. Here, EV represents these losses measured in velocity heads. Understanding how valve type and position affect these losses is key to managing energy efficiency in fluid systems. Here, we see a table outlining friction loss factors for different types of valves. Notice how the values change dramatically depending on how open the valve is. For example, a gate valve wide open has a very low loss factor, but as it closes down to a quarter open, the loss skyrockets. Globe valves, even wide open, show much higher friction losses compared to gate valves. This helps us understand how valve position impacts flow resistance and overall system efficiency. Here, we see a detailed look at how energy loss happens when a flow gradually expands. The graph plots the angle of expansion against the energy loss, showing a clear trend. As the angle increases, so does the loss. The equations on the slide break down the relationship between velocity, energy, and expansion angles, helping us quantify these effects. This is key for understanding how to design systems that minimize wasted energy during expansion. Let's take a closer look at orifice flow meters, a common tool for measuring flow rates of liquids and gases. They work by creating a pressure difference across a plate with a small opening. That's the orifice. The flow causes a drop in pressure from P1 to P2, and by measuring this difference, we can calculate the flow rate. This slide shows the relationship between pressure, flow, and factors like the Reynolds number, which tells us about the flow's behavior around the orifice. Let's talk about the Venturi tube, a classic tool for measuring flow rate through a pipe. It's also called the Herschel-Venturi tube. The key idea here is differential pressure. That's the difference in pressure between 2 points, labeled D and D on the tube. By measuring this pressure difference, we can accurately determine how much fluid is flowing. It's a simple concept, but incredibly powerful in fluid dynamics and engineering. As fluid moves through a pipe, the friction near the wall creates a boundary layer, a region where the flow slows down. This layer starts small but grows thicker as we move further from the pipe entrance. Eventually, it fills the entire pipe, changing the velocity profile. At this point, the flow stops evolving along the pipe's length and becomes fully developed, meaning the velocity no longer changes in the flow direction. This concept is key to understanding pipe flow behavior. When we look at head loss in pipe flow, several key factors come into play. It increases directly with the length of the pipe. The longer the pipe, the more loss we see. It also grows with the square of the velocity, especially at high Reynolds numbers, meaning faster flow means much more loss. Head loss decreases as the pipe diameter gets larger, but it goes up with surface roughness. Interestingly, it doesn't depend on pressure. To find total losses, we add up losses from roughness, fittings, valves, and so on. Let's break down how the fundamental principles of conservation, mass, momentum, and energy, come together in fluid flow. When we assume steady flow with constant density, these principles simplify into the Bernoulli equation, which relates pressure and velocity. Dimensional analysis then connects flow rate to pressure drop. For laminar flow, we can use these conservation laws to derive exact solutions, like the Hagen-Poiseuille equation. But turbulent flow is trickier. It relies on experimental data to understand losses and velocity profiles. Experiments also link friction factors to Reynolds numbers, showing that at high flow rates, head loss becomes less significant. This sums up the essentials of pipe flow. Here, we see two very different types of fluid flow, laminar and turbulent. Laminar flow is smooth and orderly, with layers sliding past each other quietly. Turbulent flow, on the other hand, is chaotic and full of swirling eddies. The images show these contrasts clearly, from a simulation of turbulent air coming out of a tailpipe to a laser-induced fluorescence image capturing the complexity of a turbulent boundary layer. This comparison helps us understand how fluids behave in real-world conditions. We're looking at a major project led by the city of Hammond, Indiana, relocating a massive 54-inch water main. That's a huge pipe, and it's a reminder that pipes really are everywhere beneath our feet. Moving something this size isn't just about digging, it's about careful planning, coordination, and making sure the city keeps running smoothly while the work happens. This project shows just how vital infrastructure is, even when it's out of sight. Pipes are everywhere in our daily lives, quietly doing their job beneath the surface. Drainage pipes are a perfect example. They carry away water and waste, keeping our homes and cities clean and dry. Without them, we'd face flooding and serious health risks. Today, we're going to explore how these pipes work, why they matter, and the role they play in the bigger picture of infrastructure. Let's dive in. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Pipes are everywhere. They're the hidden veins of our cities. Water mains, in particular, carry life-sustaining water beneath our streets, delivering it to homes, businesses, and public spaces. Without these crucial pipes, modern life as we know it would grind to a halt. Today, we're diving into how water mains work, why they matter, and the challenges involved in keeping them running smoothly. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Here, we see a detailed set of equations and data related to fluid flow and pressure measurements. The slide captures how variables like density, velocity, and pipe diameter come together to define flow characteristics, including Reynolds number and friction factors. It also shows how pressure differences relate to fluid height and density. This combination of formulas and values helps us understand the forces at play in fluid systems, laying the groundwork for analyzing flow behavior and resistance in pipes. Here, we see a set of equations that describe how a variable labeled F changes with the Reynolds number, Rhe. Each formula captures a different relationship. Some show F increasing as Rhe rises, others show it decreasing. These expressions help us understand complex flow behaviors by connecting friction factors to flow conditions. It's a way to predict how fluids behave under different speeds and sizes, which is crucial in engineering and science. Let's talk about dimensional analysis. It's a powerful tool that helps us check the consistency of equations by looking at the units involved. Instead of focusing on numbers alone, we focus on the dimensions, like length, time, and mass, to make sure everything lines up. This method can catch errors before they cause problems, and it even helps us derive new relationships between physical quantities. It's a simple idea with big impact. Let's talk about units and their types. Units are the standard measures we use: meters, seconds, feet, tons, and so on. But behind those units are different types, like length, mass, force, or volume. The type of unit a value belongs to is called its dimension. For example, square meters represent an area, while kilometers per hour measure velocity. Understanding these distinctions helps us make sense of the numbers we work with every day. When we work with units, it helps to break them down into their most basic building blocks: length, time, and mass. These are what we call fundamental dimensions. Units aren't just simple numbers, they can be raised to powers too. For example, area is length squared, volume is length cubed, and force combines mass, length, and time in a specific way. Understanding these powers of units gives us a clearer picture of how different measurements relate to each other. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. When we look at waves moving through shallow water, their speed depends on just two things, gravity and the depth of the water. Gravity has units of length over time squared, and depth is simply a length. So, which formula for wave speed makes sense dimensionally? One option involves the square root of gravity times depth, and the other has a different arrangement. Our goal is to figure out which expression correctly matches the dimensions of speed. Let's break down some base quantities and their dimensions. Speed is a good starting point. It's measured in kilometers per hour, combining length and time. So its dimensions are length over time. Height, on the other hand, is simpler, just a length, like centimeters. Then we have acceleration, measured in meters per second squared, which involves length over time squared. These fundamental quantities help us understand how different physical properties relate to each other. Here, we're looking at a series of formulas, each one trying to describe the same physical relationship. Some of the terms line up perfectly, which is a good sign. Others don't match quite as well, and that's where we need to dig deeper. This slide is all about checking our results, making sure the math holds up, and that the equations truly represent what we expect in the real world. It's a crucial step in validating our work. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's look at what dimensional analysis can and can't do. It's great for checking units, making sure everything lines up correctly. But it doesn't catch numeric factors, because those don't have units. So, even if the units check out, the actual equation might still be wrong. This means we can't rely on dimensional analysis alone to confirm every part of a formula. It's a helpful tool, but not a complete validation. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's talk about a machine designed to move fluid by pushing it outward in a radial direction. Imagine fluid starting at the center of a circle, then being accelerated toward the outside edge. This is exactly how centrifugal pumps work. They take fluid in at the center and use rotational force to fling it outward, creating flow and pressure. It's a simple concept, but incredibly powerful for moving liquids efficiently. Let's talk about centrifugal pumps. At the heart of this machine is an impeller, a rotating component inside a case, often called a diffuser. When liquid enters the center of the impeller, its vanes catch the fluid and speed it up as the impeller spins. This increase in velocity pushes the liquid outward, using centrifugal force, and directs it into the diffuser. This process efficiently converts rotational energy into fluid movement, making centrifugal pumps essential in many systems. Let's talk about what happens inside a centrifugal pump. There's a collection chamber built into the casing. Its job is to take the kinetic energy, that's the energy from the fluid's velocity, and convert much of it into head, or pressure. This transformation is key because it allows the pump to move fluid efficiently, turning speed into the force needed to push liquid through a system. It's a clever way to harness motion and make it useful. Let's take a moment to get familiar with some key pump terminology. Understanding these terms helps us talk about pumps clearly and avoid confusion. Whether we're discussing flow rates, pressure, or efficiency, knowing the right words makes a big difference. This foundation sets us up to dive deeper into how pumps work and how to choose the right one for any job. So let's get comfortable with the language of pumps before moving forward. Let's talk about something called head in fluid systems. It's a way to express pressure using the height of a water column, measured in feet. For example, 100 feet of water creates a certain pressure, which we can convert into pounds per square inch or psi. Here, 43.3 psi corresponds to that 100-foot head. So when you see head, think of it as the potential pressure from a column of fluid standing that tall. It's a handy way to link height and pressure together. Let's talk about how pressure and head relate in fluids. Head, measured in feet of liquid, can be calculated by multiplying pressure in psi by 2.31, then dividing by specific gravity. Conversely, pressure in psi equals head times specific gravity, divided by 2.31. Psi stands for pounds per square inch. Specific gravity compares a fluid's density to water's is 1. If a fluid's denser, its specific gravity is greater than 1. If it's lighter, it's less than 1. This helps us convert between pressure and head accurately. When we talk about pumps, head and pressure are really two sides of the same coin, as long as we use the right units. Converting all pressure measurements into equivalent head units makes calculations much simpler. It's a way to speak a common language in pump systems, helping us compare and work with different values more easily. This approach streamlines the math and keeps things consistent throughout our analysis. Let's dive into the heart of the impeller, the eye where water enters. The impeller vanes play a crucial role here. When the impeller is thicker, it moves more water. Increasing the diameter boosts the pressure, and speeding up the impeller ramps up both water flow and pressure. These centrifugal impellers rely on thickness and diameter to control performance. It's a delicate balance. Each factor directly impacts how efficiently water moves through the system. Let's talk about how direction of flow changes when we double the pressure, but keep the water volume the same. The key here is using two impellers in series. By stacking them this way, we boost the pressure without increasing the flow rate. It's like giving the water an extra push, twice the force, while maintaining the same steady stream. This setup is crucial when higher pressure is needed without changing the amount of water moving through the system. Let's talk about the direction of flow and how it affects performance. When we place impellers in series, we're essentially stacking their power. This increases the total head produced, which is just a way of measuring pressure. The total head equals the number of impellers multiplied by the head one impeller creates on its own. So, more impellers in series means more pressure, and that's key for many applications. Let's talk about the pump performance curve. This graph shows us how a pump behaves, how much head it can generate against the flow it delivers. It's a vital tool for understanding a pump's capabilities, helping us match the right pump to the job. As flow increases, the available head usually drops, and that relationship is what this curve maps out. It's a simple line, but it tells a complex story about efficiency and power. Let's start by looking at the pump's flow rate. This is shown along the horizontal axis, or the x-axis. It tells us how much fluid the pump moves, usually measured in gallons per minute. This is the first step in understanding the pump performance curve, giving us a clear way to track how the pump behaves as flow changes. It's a fundamental piece of the puzzle. Let's talk about the vertical axis on a pump performance curve. This is where we plot the head the pump produces. Head is basically the height the pump can raise water, and we usually measure it in feet of water. This vertical axis gives us a clear way to see how much pressure the pump generates at different flow rates. It's a key part of understanding pump performance, and it's our second step in reading the curve. Let's talk about pump performance curves. Most of these curves slope gently from left to right, showing how the pump's head changes as flow rate increases. The head represents the pressure the pump can generate, while the flow rate is how much fluid moves through it. Step 3 in our process is all about mapping these two key factors, flow and head, so we understand exactly how the pump will perform under different conditions. This curve is the foundation for making smart decisions about pump operation. Let's talk about shutoff head. This is the maximum pressure a pump can generate when there's no flow at all. In other words, the pump is running, but nothing's moving through it. It's a key point on the pump performance curve, showing the limit of pressure the pump can build. Understanding shutoff head helps us know how the pump will behave under different conditions, and it's essential for matching pumps to the system they serve. Let's talk about maximum flow. This is the highest flow rate a pump can deliver. At this point, the pump isn't producing any head, meaning there's no pressure difference being generated. It's all about volume, not force. On the pump performance curve, this is a key point to understand because it marks the limit of flow capacity. Knowing this helps us see how the pump behaves under different conditions and why flow and head are always in balance. Let's talk about the system performance curve. This curve maps the relationship between the head, or pressure, needed to move fluid through a system, and the flow rate it produces. When we say system, we mean everything the fluid passes through: pipes, fittings, valves, and other devices. Each of these adds friction, which creates resistance or head loss. So the curve shows how much pressure you need to overcome that friction and keep the fluid flowing at different rates. It's a crucial tool for understanding and designing fluid systems. Let's start by looking at the system's flow rate. This is what we plot along the horizontal axis, or x-axis. Flow rate tells us how much fluid moves through the system over time, and it's usually measured in gallons per minute. Understanding this helps us see how the system performs under different conditions. This is the first step in building the system performance curve, giving us a baseline to compare against other variables. Here, we're focusing on the vertical axis, the y-axis, which shows the head the system requires. Head, in this context, is usually measured in feet of water. It tells us the pressure the pump needs to generate to move fluid through the system. This axis is key to understanding how the pump performs as flow changes. So, step 2 in our process is all about plotting this head on the vertical axis, setting us up to see the system's performance clearly. Now, let's talk about friction loss. This is the resistance the fluid faces as it moves through the system. We map that friction loss onto a graph, alongside pump flow rate and head. The key point is that friction loss changes depending on how much fluid is flowing. In step 3, we use this information to create the system performance curve, a visual tool that shows how the system behaves under different conditions. It's a crucial step for understanding overall performance. The operating point is where the system curve meets the pump curve. It's the spot that tells us how the pump and the system work together in real time. At this point, the flow rate and the head are balanced, meaning the pump delivers exactly what the system needs. Understanding this intersection helps us predict performance and optimize efficiency. It's a crucial concept for anyone working with pumps and fluid systems. Now let's focus on pump selection. We're looking at 3 circulators, circulator 1, 2, and 3, each playing a role in moving fluid through the system. The key factors here are the pump flow rate, which tells us how much fluid is being moved, and the head, which is the pressure the pump needs to overcome. Balancing these ensures the system runs efficiently and reliably. When we adjust the amount of friction loss, or what's often called throttling the pump, we directly impact how the pump performs. This method lets us control the flow and pressure without changing the pump itself. It's a simple but powerful way to fine-tune performance, especially when conditions vary. Understanding this gives us more control over the system's efficiency and reliability. Let's talk about pump selection, starting with how valves affect flow. When the valve is barely open, the flow is restricted. The pump works harder against resistance. Partially open valves allow more flow, but still limit the system somewhat. When the valve is fully open, the pump can deliver its maximum flow rate. 2 key factors guide our pump choice: the flow rate we need, and the head, that's the pressure the pump must overcome to move the fluid through the system. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Let's look at some key heuristics for sizing pipe diameters. We use the diameter, mass flow rate, and density to estimate the right pipe size. For liquids, the diameter scales with the mass flow rate raised to about 0.5 power, adjusted by density. For gases, the relationship is a bit different, involving both flow rate and density with specific exponents. These equations give us a practical starting point for piping design, balancing flow needs with physical constraints. Here, we're looking at the fundamental equation for energy loss in piping systems carrying incompressible fluids. It ties together pressure, velocity, elevation, and losses due to friction or fittings, all expressed in consistent units. The equation balances energy at 2 points along the pipe, accounting for head loss, which represents the energy lost as fluid moves through the system. Understanding each term helps us predict how fluids behave under different conditions, which is crucial for designing efficient piping networks. Let's break down how sudden changes in pipe diameter affect flow. When the pipe suddenly enlarges, there's a specific loss coefficient, K, that depends on the ratio of diameters. For straight pipes, K relates to the friction factor and pipe length. The volumetric flow rate, Q, and pipe diameter, D, are key variables here. We sum all the fitting losses to understand the total impact on flow. This helps us calculate head loss, which is critical for designing efficient piping systems. When fluid flows through pipes, fittings like elbows and T's create resistance, which we call friction loss. This table shows us the friction loss factors for common fittings. For example, a standard 90-degree elbow is equivalent to 30 feet of straight pipe, while a 45-degree elbow is about 16 feet. T's have different values depending on flow direction, 20 feet for the run and 60 feet for the branch. Pipe entrances and exits also have factors, slightly less or equal to 1. Understanding these helps us design efficient piping systems. Let's talk about friction loss factors for valves, a key concept when we're dealing with fluid flow. The valve coefficient, or CV, helps us understand how much resistance a valve adds to the system. It's calculated using this formula, where K represents the friction loss factor. Different types of valves have very different K values. For example, a gate valve has a low factor, while a lift check valve creates much more resistance. Knowing these numbers helps us design systems that work efficiently, with the right valves in the right places. Here, we see a formula that connects several important variables, diameter, roughness, and Reynolds number, to calculate friction factor in fluid flow. This equation helps us understand how resistance changes with different conditions inside a pipe. It's a key part of the fanning diagram, which engineers use to predict pressure losses and optimize systems. By breaking down these relationships, we get a clearer picture of how fluids behave in real-world situations. Let's talk about how valve type and position affect flow. Valves create a complex path for fluid, which often leads to high head loss. That's actually part of their job, to restrict flow when they're not fully open. We measure these losses in velocity heads, represented as EV. Understanding this energy loss in valves helps us design systems that balance control with efficiency. It's a key factor in managing fluid dynamics effectively. Let's wrap up our discussion on the Pelton wheel. It was the first concept developed with scientific backing, and it even became a patented product. It's the only real option when you're dealing with very high heads, above 600 meters. It's best suited for low flow rates paired with moderate heads, somewhere between 240 and 600 meters. It's also a solid choice when you have moderate heads and medium flow rates. One of its biggest advantages is how easy it is to build and develop, since it operates at constant atmospheric pressure. But it does have a drawback. Low revolutions per minute at moderate or borderline heads can be a challenge. Let's explore whether pure momentum can be applied to low head jets. This question is key because low head jets behave differently from other flows. Understanding if pure momentum works here helps us know its limits and where it might need adjustment. We're diving into the specifics of flow dynamics, looking for where this approach fits best and where it might fall short. It's a crucial step in refining our models and making them more versatile. Let's take a closer look at the turbo turbine. It's a type of impulse turbine designed to handle medium heads and flow rates. What makes it stand out is the way water hits the blades at an angle, allowing for higher speed and efficiency compared to traditional impulse turbines. It's a smart choice when you need to balance power output with a compact design. The turbo turbine is a great example of engineering that adapts to specific site conditions. Let's take a closer look at the cross-flow turbine. This design is unique because water passes through the turbine twice, first across the blades, then back again. It's efficient, simple, and well-suited for small to medium-scale hydro projects. Cross-flow turbines handle variable water flow well, making them reliable in changing conditions. They're a smart choice when you need consistent power without complex machinery. Let's explore the different variations of cross-flow turbines. These turbines come in several designs, each tailored to specific water flow conditions and efficiency goals. By adjusting blade shape, size, or arrangement, we can optimize performance for everything from small streams to larger rivers. Understanding these variations helps us choose the right turbine for the right site, making the most of available energy with smart, adaptable technology. Now let's focus on specific speed. This isn't just about moving fast, it's about finding the right pace for the task at hand. Sometimes, speed means quick decisions and rapid action. Other times, it means steady progress without rushing. The key is matching your speed to the situation, so you stay effective and in control. We'll explore how to identify and apply the right speed in different contexts. This part focuses specifically on situations where flow rates are relatively low. It's important to keep in mind that the methods or principles we're discussing here work best under those conditions. When flow rates increase, different factors come into play, and other approaches might be needed. So, for now, let's concentrate on what applies when the flow is on the lower side. The textile industry played a crucial role in sparking the development of large hydroturbines. As factories grew, they needed more reliable and powerful energy sources to keep machines running smoothly. Water power was abundant, but harnessing it efficiently required bigger, stronger turbines. This demand pushed innovation forward, leading to the large-scale hydroturbines we know today. In other words, the rise of textiles helped shape the future of renewable energy technology. Originally, textile mills relied on water wheels or breast wheels, turning as water filled them. These wheels were fairly efficient, about 65%, but they had a major drawback. Backwater would build up and stop the wheel from turning properly. This slide shows the shift from using less effective fluid mechanics to adopting better, more efficient designs that solved these issues and kept the wheels turning smoothly. Let's talk about Francis turbines, a type of reaction turbine named after Sir J.B. Francis, an English-born American engineer. Water enters the turbine from the outside, moving radially, then leaves axially, which is why it's called a mixed-flow turbine. Only part of the water's energy converts to velocity before hitting the runner. Pressure drops as water moves over the blades, creating reaction pressure that helps spin the runner. These turbines work best with medium heads and a good flow of water. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. A brief transitional moment here as we move between sections of the presentation. Let's continue forward to the next topic, which we'll explore in more depth. Now, let's turn our attention to the Francis installation. This part of the project brings together innovation and art in a way that's both striking and meaningful. It's more than just a display, it's an experience designed to engage and inspire. We'll explore how this installation fits into the bigger picture and why it's a key element in our overall vision. Let's take a closer look at the Francis turbine. It's one of the most widely used turbines in hydroelectric power plants around the world. What makes it special is its versatility. It works efficiently across a wide range of water flow and head heights. The design channels water through curved blades, converting energy smoothly from water into mechanical power. Understanding the Francis turbine helps us appreciate how we harness nature's energy with precision and reliability. Let's take a look at the Francis runner. It's a traditional runner design, something many are familiar with. Alongside it, we have the X-Blade runner, a more modern take that offers a different approach. Comparing these two helps us understand how design evolves, balancing heritage with innovation. Each has its strengths, and seeing them side by side sets the stage for what comes next. Let's explore the Francis turbine power plant, a remarkable example of a continuous hydraulic system. This setup harnesses flowing water to generate power in a smooth, ongoing way. Unlike systems that work in bursts, the Francis turbine keeps energy moving steadily, making it efficient and reliable. It's a key technology in hydroelectric power, converting water's force into electricity without interruption. Understanding this system helps us appreciate how water can be a constant source of clean energy. This slide introduces an active Pascal law, framed as a hydraulic model specifically for Francis units. It's a way to understand how pressure and fluid dynamics interact within these turbines. By thinking about it hydraulically, we get a clearer picture of how forces balance and flow behaves, which is crucial for optimizing performance. This model helps us bridge theory with practical engineering in a very tangible way. Let's take a closer look at the parts of a Francis turbine. This type of turbine is a workhorse in hydroelectric power, known for its efficiency and versatility. Each part plays a crucial role, from the spiral casing that guides water in, to the runner where the energy transfer happens. Understanding these components helps us see how water's force is transformed into mechanical power, driving turbines that generate electricity for millions. Here, we're looking at the maximum opening position of the guide vanes within the runner inlet. The runner inlet has a diameter of 0.87 meters, while the guide vane outlet is slightly larger, at 0.913 meters. The guide vanes themselves are arranged evenly around the circumference. Their position and angle are crucial. They control the flow of water entering the runner, directly impacting efficiency and performance. This setup shows the vanes fully closed, ready to adjust as needed. Let's talk about how guide vanes operate. When fully open, they reach an angle of 18 degrees. At the design position, which is where they typically work most efficiently, they sit at 12.21 degrees. Of course, they can also close completely when needed. These positions control the flow and direction, making sure everything runs smoothly and efficiently. Understanding these angles helps us grasp how the system adapts to different conditions. Here, we're looking at the flow of water particles as they move through the spiral casing. The focus is on the radial view of the runner, along with the guide vanes and stay vanes. These components work together to direct and control the water's path, ensuring efficient energy transfer. Understanding this interaction is key to grasping how turbines convert fluid motion into mechanical power. It's a detailed look at the heart of the system in action. Let's take a closer look at the parts of a Francis turbine. This type of turbine is a workhorse in hydroelectric power, designed to efficiently convert water flow into mechanical energy. Each component plays a crucial role, from the spiral casing that directs water to the runner where the blades capture energy. Understanding these parts helps us appreciate how water's force becomes electricity, powering homes and industries around the world. Now, let's look at hydraulic efficiency in a Francis hydraulic system. This equation shows how we compare energy at different points, factoring in velocity and height, while accounting for losses along the way. Essentially, it measures how well the system converts the available energy into useful work, highlighting where energy is lost due to friction or turbulence. Understanding this helps us optimize performance and reduce waste in hydraulic machinery. Let's talk about the different types of losses that can impact efficiency. We have gap losses, which happen where parts don't fit perfectly. Runner losses occur within the moving blades themselves. Draft tube losses come from the flow as it exits the turbine. Then, friction losses happen in the spiral casing and the stay vanes, where surfaces rub against the fluid. Finally, guide vane losses take place as the flow is directed into the runner. Each of these plays a role in how much energy we actually capture. Let's talk about hydraulic efficiency in Francis turbines. This slide shows how energy moves through the system, starting with the head, which is the height of the water driving the turbine. Some energy is lost along the way, especially in the draft tube, where flow slows down and pressure changes. These losses reduce the overall output energy, so understanding and minimizing them is key to improving turbine performance. It's all about squeezing the most power from the water's force. On this slide, we're looking at the key factors that affect how efficiently a Francis turbine converts energy. Output percentage shows how much power we actually get from the turbine. Output energy reflects the usable energy produced. Hydraulic efficiency measures how well the turbine converts water flow into mechanical energy. And finally, losses remind us that no system is perfect. Some energy is always lost due to friction, turbulence, or other factors. Understanding these helps us optimize turbine performance. To wrap up, the spiral casing, also called the scroll or volute casing, guides fluid from the penstock and surrounds the runner completely. Its design narrows evenly around the circumference, keeping fluid velocity steady as it moves toward the guide vanes. This ensures efficient, smooth flow right where it's needed most. This video was created with SlideSpeak. Visit SlideSpeak to turn your presentations into engaging AI-narrated videos.